Okay, welcome to the second lecture of the neural engineering week in the course. Today, as you can see, we're going to be talking about neural transformations. So last class or video, we talked about how you can take numbers or vectors of numbers and encode them in the collective activity of a population of neurons. And we showed how you could decode those values back out by finding the optimal linear decoders. And you can actually decode out nonlinear functions of the things that were encoded in that population. So the goal in this lecture now, though, is to see how to use population coding to pass data between populations of neurons. So far, we've only looked at interpreting the activity of a population of neurons, decoding its encoded values to an imaginary readout node. But of course, in brains, there are not imaginary readout nodes. Instead, neurons send their output to other neurons. Okay, so the whole decoding thing is kind of a convenience for us to understand what the neural network's doing, but really what we want is populations of neurons communicating with other populations of neurons, doing processing as you go down the line. And at some point, maybe a population of neurons causes some sort of motor output or some sort of storage event or whatever, and some sort of behavior. Okay, but for now, we're going to talk about transforming data from one population to another. So suppose we want to encode the same value that's encoded in A, encoded in B. Suppose we want to encode, I'm reading now. Suppose we want B, population of neurons, to encode the same value encoded in A. So let me draw a picture since I brutalized that sentence. So here's population A. And we've got all these inputs. I guess encoders. So we've got some input here. We're encoding some value or some vector values. Just to say for the sake of argument, some value. We want that value to be encoded in a population B. And so these are all connected, of course. And then from there, we'd like to decode out what's in B. So the question is, how do we take what the value that's encoded in A, using population coding, to copy it to being encoded in B? Again, population coding. So one answer, or one possibility, is to copy the neural activity. So we say, well, why don't we let B1 activity equal the same as A1? B2 be the same as A2, and so on. Why don't we just copy the neuron activities directly over? Well, of course, that only works if you have the same number of neurons in population A and population B. That we can't assume that in general. So what other alternatives do we have? Well, I guess the answer to the question, can we just copy the neural activities, is no. No, A and B might have different numbers of neurons. So generally, you can't do it that way. So here's a different approach. I'll switch to using a smaller pencil thing. Here's a different approach. So if we want to copy the value that's encoded in A to be encoded in B, one thing we can do is whatever's encoded in A, decode it. So if X was encoded in A, we're going to decode an approximation of it, X hat. And let's say those decoding weights are D sub A. So these are the identity decoding weights for the population A. Identity decoding because it's just decoding the value that was encoded in there. So it's really like decoding the identity function applied to what was encoded. So once we have the X hat, we can now encode that in B. And let's say the encoding weights and biases are, well, the encoding weights, I guess, are represented by E sub B. So now B will have encoded the value that was decoded from A, which presumably is the same value that was encoded in A. So here I'm talking about k vectors, by the way. It doesn't have to be just scalars. It can be vectors, whatever. But in summary, let me just write down this idea. To copy the value we essentially decode it from A and then re-encode it using B's encoders. That's that whole process there. So let's go through that step by step, because I want to sort of show one way of thinking about what's going on here. So I'm going to be talking about two different spaces. You see, when we've got, this is a common thing that comes up. X can be a vector. X can be a vector. It's going to be a k vector. But also the activity in the population can be represented as a vector. So these are two different vector representations of the same thing, though, right? So we can, from the vector of activities A, we can decode, actually it would be a row vector, we can decode from that what was input, okay? So two different ways of representing the same information. So I call these the data space and the neural activity space. Activities, I won't write space. Data space and neural activities. Two different vector representations of the same thing. Okay, so now when we go to the first stage and we encode X into A, we basically get A, now that's a vector of activities of population A. It's, well, some nonlinearity applied to the input current. Okay, so these E sub A, those are the encoding weights, the weights that go in. These are the biases for that population. And then this is like some activation function, like a LIF tuning curve or logistic or whatever. Now, just to help out with what's coming next, let's write down the dimensions of these things. So this X vector is a 1 by K input vector. So the encoders have to be K by N, because we have N neurons in the population A. And beta needs to be 1 by N, because it has to match the output of that operation there. Okay, so what we get out of this is 1 by N vector. So A is a 1 by N vector, row vector. So over here, X is in our data space. It's kind of like our imagined data, right? It's the sort of the more abstract version of the processing we're doing. Of course, that vector gets encoded into neural activities, A. I'll call the matrix, or the vector of activities A. Oh, as I did over here. So encode using the weights EA. Great. So we've gone from data space into the neural activity space. Now to decode the value from A, we use the optimal linear decoding weights, which presumably were solved for using least squares. So then we get X hat equal to A times, I'll write it as DA, the decoding weights for population A. You'll notice that I'm not using the transpose anymore. It might have been a mistake to put the transposes on the last population coding lecture. It doesn't really matter whether you store D as itself or the transpose. I don't want to dwell on that. So I'm just going to drop the transpose now, and I don't think it'll hurt anybody. Having said that, now let's write down the dimensions of things. A, as we said above, is a 1 by N matrix, and for dA to do the right thing, it's got to take that N row vector, turn it into a K vector, so this has to be N by K. So that this thing out here is 1 by k. Has to be, because our original x was 1 by k, so an estimate of it should be also 1 by k. Okay, so what's going on here over in the data space and neural activity space? What's happening is we're coming back to the data space by doing a decoding. Decode using d sub a, and we get our x hat. Okay? All right, so now let's say, looking back at this figure up here, now we have to re-encode it into the population B. So what does that look like? That looks like B equals sigma of x hat times the encoders for B plus the biases for B. Now again, looking at the dimensions, this is 1 by k. This is k by m, because now this population B we're saying has m neurons. It was actually up here. N neurons and m neurons. And of course, then this must be 1 by m to match. So this whole thing must be 1 by m. Great. So over here in the picture, we're re-encoding using E sub B into another set of neural activities. Now, of course, this is A was 1 by N, B is 1 by M. They're different size spaces, different dimension spaces, so they don't really represent the same vector space. A and B, they're not in the same vector space. But they're still neural activities. They're vectors of neural activities. So I put them both on the neural activity side of the line there. Okay, so, but here's the interesting thing. We can actually go directly from A to B in a way without going through x hat. So let's look at the algebra here. We've got sigma of x hat times EB. But what was x hat? X hat was A times the decoders of A. It was the activities in A times the decoders of A, which then got encoded into B again, plus the biases. Now, we can put the decoders and the encoders together into a single matrix and call it W. Sigma of A times W plus the biases, where W equals the decoders for A times the encoders for B. So let's look at the dimensions of this thing. dA, the decoders for A, were N by K. The encoders for B were K by M. So that means W is N by M, which one might expect. So this W really is a set of connection weights that go from A directly to B. So you don't actually have to decode x hat and store it somewhere and then take that x hat and then re-encode it using the encoders of B. You can actually just multiply the activities in A by this weight matrix W directly to get the input current for the neurons in B. And then, of course, if we want, we can decode from B using its decoders. So I'll call it X double hat. Thank God we're not doing more populations because this can get awkward. Okay, and those D sub B, those optimal linear decoders for population B could be solved for using least squares, the same deal. Okay, so even though the idea is to decode it into x hat and then re-encode it, can actually be implemented just using a single weight matrix. And that's what the neurons, if you actually had neurons, that's what they would be doing. Okay. The reason we connect populations of neurons is because connections can perform transformations on that data. So given a population encoding xy, let's say, we want to build a network that computes x times y. Now, I showed you how you can compute the decoding weights before. So let's just, what color should I use? How about green? I'll use red. So I'll use the other colors. So we have the encoders EA. Now EA is a matrix, since it's decoding from R2 into A, from 2 inputs into n inputs, these encoding weights are going to be a matrix with 2 rows. It's kind of like 2 sets of encoding weights. And then we get our hidden population activity A, the vector. It's got n neurons in it. And then we decode from it using dx, I'll call it dxy, but it's a set of decoding weights. You can see there are just n decoding weights that together, when you multiply those by the activities in A, you get an estimate of x times y. I explained this last lecture. And then you can encode those into B. So now population B with m neurons is encoding x times y. Quick joke. A man's out driving with his son, and his son turns to him, "Dad, what's an alcoholic?" And the dad, he thinks about it. "Okay. All right, son, see out in front of us. See those 4 cars? Well, an alcoholic would see 8 cars because they see double." And the boy says, "But Dad, there are only 2 cars in front of us." Okay. So I outlined this this population A projecting to population B, and this set of connections is computing the product of x times y. This vector that was encoded in A, xy, through this set of connections to B is encoding the product x times y. So just to make sure you know what dxy is, it's the arg min over d of A times d minus x times y. I actually had them right, I guess. Okay. So I've written it up here as decoding again to a single value, scalar value, then a re-encoding. But again, that could be just a single full matrix. And so that set of connection weights actually carries the product x times y and re-encodes it in B. So that set of connection does the computation of multiplying the 2 components that are stored or represented in A. So this is one of those cases where there's a low dimensional matrix product, sorry, a low rank matrix product. It's a low dimensional bottleneck. So even though we can form a full connection weight matrix, as I just described, the decoders times the encoders, get W out of it. So even though we can form a full connection weight matrix W from the product, D times E, it's actually a low rank matrix. Okay, so in the example above, dxy was n by 1 because it was decoding from n neurons. And E sub B was 1 by m because it's encoding a scalar into m neurons. So W was this n by 1 times this here, I'll make m a bit bigger, to give us this full n by m matrix. So this is a rank 1 matrix product, n by m. outer product, if you like. You could think of it as an outer product, but it's when you are explicit about whether we're dealing with row matrices or column matrices, it turns out into just outer product is just a normal matrix product with the dimensions the way they are. Okay. So this might seem like a limitation, that the fact that you're taking these low dimensional vectors and you're forming this full matrix, but it actually makes things more efficient. So we could implement them with a full weight matrix W, and if you actually had a fully parallel machine like a brain or maybe a neuromorphic hardware where all the neurons actually do operate in parallel. They're not running on this, you're not being simulated on the same processor. They're all actually sending connections at the same time. In that case, the full weight matrix W is perfectly efficient because all those connections are being run simultaneously. But if you're on a CPU or maybe even on a GPU and you just have a limited number of processing units, this low rank matrix factorization is actually helpful. And here's why. So let's think about how many flops it takes to multiply A times the full weight matrix W. So A is going to be some row of activities. There are going to be n elements in it. And W is this n by m matrix, n by m. So the number of flops equals, well, for every single element, for every column in W, you have to form this sort of inner product of A with that column, right? That inner product has on the order of n flops, and you have to do m of them. So it's n times m, or in the order, maybe I should say order of nm flops. Now, how many flops does it take to multiply A times D times E? DE was the same as W, right? But if we keep it factorized into its D and E, the sort of rank 1 factors, we can do it more efficiently. So we've got A, like we did before. Now instead of writing W, we write DE. So D looks like that, and E looks like this. So it's this bizarre product we're doing. There's n of those. That's A, that's D, and this is E with m elements in it. So what we're going to do is do this product first, the A times D. Well, that's an inner product. You just get a scalar out of that. Then we have to multiply that by E still. So to get this, the flops was order n. Right, the inner product between two vectors of n elements is order n. So I think probably 2n minus 1 or something. And now there's this, we have to multiply by this, that scalar, which is AD, times the vector E, which is just order m flops. So the total flops is order n plus m. So that's a lot cheaper than order nm as n and or m get larger. So if you're implementing this in an actual brain, you have the full weight matrix, but it's run in parallel. If you're running this on a finite number of CPUs or processing units, you can actually take advantage of this low order or low rank factorization. So let me demonstrate that in Nengo. So here's something that we looked at last video. It's a population encoding 2 values. So I can change each of, this stim here is just this input thing. This thing here is showing the decoded values from this population of 50 neurons. Okay, so let's add another population. B. B equals Nengo ensemble number of neurons equals 30, let's say. Dimensions equals 1. So we're going to have A is a two-dimensional population, so it encodes like an XY vector. B is going to encode just one number. So we're going to connect A to B, but the function that the connection is going to compute, I can give it here. Lambda x, so I'm going to say x0 times x1. So that's like an inline function, a lambda function. So this connection here, I didn't place it very conveniently. This connection here from population A to B has connection weights set so that it decodes x, basically x times y from A, and then re-encodes that value into B. So now let's look at the value encoded in B. So as usual, Nengo automatically computes the identity decoders. So what we'll see here is just the single value encoded in population B. Now, right now, the two values encoded in A are both zeros. So 0 times 0. If I change one of them to be non-zero, that's great, but still something non-zero times 0 is a 0. So we're still seeing 0 encoded in population B. Nothing happening. It's for both of these. Nothing happens. But if I make one non-zero and the other one non-zero, now we start to see things in population B change. Let me make one of them a negative. So A is encoding -1 and this other value. So let's see what's in B. It's basically the opposite of this green line here. And it's more or less a product. It's not perfect because I'm not using many neurons. It's only 50 neurons encoding this 2 vector up here, and 30 neurons encoding this second value here. But you can see, I think you can convince yourself that it's encoding the product between those two values. So this is the story of how the idea of population coding and decoding from these populations can be used to put a chain of computations together where when you encode something in one population, you can decode that. You can decode something and re-encode that product or that new transformed data into the next population. You can build whole formulas or whole programs, I guess, by putting together chains or even networks of populations of neurons. Okay, so after this video, we'll move on to talking about the dynamics. So these populations, you can actually connect an ensemble to itself and have that recurrently connected population of neurons run a dynamical system. See you then.